Hi, I'm Peter Wieland. I'm a software development engineer in the Windows team. I've worked on the device apps, and I actually own the custom device access. Sorry, it's either device or driver. We changed the name like 5 times. Sample that's in the on MSDN, and I'm going to talk today about the WDF custom driver design pattern. So the custom driver design pattern. Talk a little bit about what that is. I have a really simple example we can sort of talk through. I'll talk about the 4 components that make up this pattern. George introduced those when he spoke a couple days ago. The device, the custom driver, the application, and the device metadata. We have some design guidance, and then we can do questions, and I can do a code walkthrough of a sample. So the custom driver pattern is sort of the catch-all pattern. If you remember the other patterns that George presented, you just did one UPnP, there's storage. Most of the other ones self-select. If your device is of a particular type of technology, then there's a pattern. For a lot of them, there's a pattern that matches. For example, if it's a network attached device, the storage pattern, the custom driver pattern are pretty clearly not the right ones. The networking pattern is either UPnP or private discovery are the obvious choices. For devices that don't fit into one of those categories, we have the custom driver pattern. What it means is that we don't have WinRT APIs that allow you to access your device, whatever it may be. If we don't have those APIs, you can provide your own driver, you define your own interface, and then your app can talk to your driver. Does everybody know what a device driver does? I hit a lot of crowds where they don't. But basically it's a broker. It's a trusted operating system component. It allows clients, be they operating system, applications, services, or other device drivers, to talk to your device. For this pattern, we support pretty much any protocol that you could write a driver for. It only supports the restricted access model, and the APIs to, I left some parentheses in there. The APIs to access it are the create device access instance function, which gives you back an iDevice IO control interface, and then you can use that to talk with your driver. Now, this pattern has a number of trade-offs. It's probably the most flexible of the pattern in terms of what type of device you can adapt it to. It's going to meet the broadest range of needs. But on the flip side, it means that you have to develop, certify, test, and maintain a custom driver, and there's a very large expense associated with that, just in terms of man hours needed to get that thing solid and shipped and out the door. It's a pretty extensive process. It supports the restricted access model, so you can do a vertical app. You can know that your app is the only thing that can talk to your device. At least in the Metro world, desktop apps can still potentially access your device. But it only supports that pattern. So if you wanted to have multiple applications that can talk to your device, you can't do that through this pattern. The other advantage on this pattern is if you already have a driver, if you already have a Windows 7 solution that uses a custom driver, that driver is probably pretty easily adaptable to this pattern. The downside, this is, like I said, it's a very complicated pattern. Not only do you have the cost of developing everything, but this has a lot of moving parts. You have a driver you have to distribute, you have metadata you have to distribute, you have the app you have to distribute. So that's 3 things that could potentially get out of sync on a customer's system, and there's a little bit more chance for things to get mismatched. There are ways to cope with that, but it requires more design and engineering effort. The communications, the portion of your app that wants to communicate with the driver has to be written in C++. Doesn't mean your whole app has to be C++, but you have to have some core C++ object that will provide the communications between your application and your driver. And the sample we have for this pattern, we have it in all 4 languages. So we have a Visual Basic, C#, and JavaScript ones, which use a WinRT component to do that communication. And then we have a C++ app, and actually all 4 of those apps use the same component. And then the last disadvantage, I guess it depends on the device and the scenario and who your customers are, but this is not a pattern that's supported on WinRT for IHVs. It's a deal that has to do, question? You can own your option. Sorry, the question was, thank you for the sign. The question was, what do I mean by only vertical solutions are supported? So it's the restricted model. So you can write one application that talks to your device through your driver to your device. You cannot fan out and have 5 or 6 different apps from different companies that all talk to your device through this pattern. If you need that, then you need to go with one of the patterns that supports open access, which would be storage or one of the networking patterns. Keyboard. So my simple example of this pattern is a USB credit card reader. Right? Customer buys a credit card reader, gets it from Amazon, and gets it from your website or, I don't know, Fry's. Plugs it in their computer. Windows will identify the device. It'll go to Windows Update and download your driver. It'll go to the WMIS server and download your device metadata. Your device metadata tells Windows which app to go get. It'll go get the app automatically. The user gets a little toast on their screen that says you have new apps, and your app shows up on their start screen, and when they click it, now you can use your app to walk them through all of your initial provisioning process. So if you need them to sign up with a web service or something like that, that can be the first few things that your app do. So in this scenario, you don't have to necessarily download the application automatically from the store. You could have your app be something that somebody goes finds. So in your application, when it loads, would use the Windows Devices Enumeration APIs, which lets you go find any device in the system. You'd use it to find your device, and then you'd use these device access APIs to communicate with the device. To be more specific, you'd use those APIs to communicate with the driver, who then runs the device. So the first of these components, the most important one probably, is the device itself. Like I said, this is a very flexible pattern. You can apply this pattern to pretty much any device. Other patterns may be a better fit depending on what your device is, but this one can be applied anywhere. We have a few requirements on the device. The first has to have some sort of unique hardware ID. For USB, this is a unique USB VID-PID combination. I believe there are similar identifiers, bus identifiers for Bluetooth. I don't know the acronyms for them. But we need a way to uniquely identify your device from everybody else's device. We need that because we have to download the metadata for the device, and we have to download the driver for the device. And if you, as an example of something we've seen, if your device uses a USB to UART bridge chip in order to put some logic on the USB bus, and you're still using the hardware ID from the company who developed the bridge chip, then we can't download your driver for that device. We could download FTDI's serial driver, but that's not configured for your device. Your app won't be able to talk to it, and we won't be able to get your metadata, so we won't be able to privilege your app to talk to the device. So it's very important when you're developing devices. If you want to use this pattern, you have to have a unique hardware ID. The second requirement, grammatically incorrect, is that the device has to pass Windows hardware certification. There's tests in there for pretty much every class of device, including unclassified, which a number of things fall into, but this is how we ensure that devices work well with Windows. And then the last requirement is that this pattern is for real external devices. This pattern is not intended to be used for virtual software devices. There are a lot of solutions in Windows that people have developed device drivers in order to allow applications to work with software components that modify the kernel or do other things, and we do not. That's not the point of this pattern, and that's not supported. So the second component is the device driver. This is the WDF custom driver pattern, so we'd really recommend your drivers be written using the Windows Driver Framework, WDF. We have a user mode and a kernel mode version of this framework. And I did a talk at Build. I have a link in the slides, and this is the title, Using the Windows Driver Framework to Build Better Drivers, where I spent more time talking about why WDF is the right way to write drivers. There are a number of companies that provide training and contracting support for writing Windows drivers as well. Unfortunately, writing a Windows driver is not a 45-minute topic, so not really including a lot of content about it here. Like I said, the point of the driver is to give the communication between the app and the device. So when your driver loads, the way it advertises its presence to any software component is to create a custom device interface. This interface has a GUID. It's like an interface ID in COM. It says, This is the contract my device supports. Driver can register multiple interfaces for multiple contracts. For at least one of those contracts, if you want your app to be able to talk to it, you have to set the restricted property on the interface after you've done this. This is what tells Windows that a Metro-style app can access this interface. And then once you've done that and the app has opened up the interface, there's some privileging things that have to happen as well, but once the app opens that interface, it can communicate with the driver by sending I/O controls. I/O controls are basically driver-specific commands. It's a 32-bit control code and then an arbitrary input buffer and arbitrary output buffer. One note is that these interfaces, we only support I/O controls for Metro-style apps. So Windows also supports read and write. Drivers can support read and write for anything that's been opened by a client, but we don't provide APIs for the Metro-style app to do read and write on those handles. Like I said, you have to pass through certification. As part of going through certification, your driver will get signed, and then you can upload your driver to Windows Update. The usage model we really want is the user buys your device, plugs it in, and everything automatically downloads and works. To do that, we need to get your drivers on Windows Update. We do not really want user plugs in your device, then has to go on the web, find your drivers, run some installer that does God knows what to the system, no offense, and then the device works, and then they can go get the app. That's really not an ideal thing for an end user. And another question that's sort of come up a lot that I want to just be clear on is, when we say you have to write a custom driver, it doesn't mean that that's the only driver involved in the chain. For example, if you have a USB device, you write a custom driver for the USB device, but we have a whole USB silo that runs the USB host controller that gets commands from that USB driver out to the device. Likewise, if your device is a HID device, you can write a driver that loads on one of the HID collections exposed by the device. So you can leverage our inbox software for our standard inbox class drivers for HID, even for like mass storage API if you wanted. Although then you wouldn't be a mass storage device anymore. But you can leverage our inbox class drivers and layer your own drivers on top of them in order to make use of that functionality. So third component, also kind of fundamentally important in this, is the app. The application, there's really, I mean, your application can be any regular Metro app. Can be written in any language you want, doesn't matter. The only requirement, as I said, is you have to have some C++ code to do the actual device access. So the requirements are that your app declares a custom device interface class and its capabilities. So whatever interface class GUID you published in your driver, that's the interface class you have to declare in your app. You can declare multiple of these if you need to talk to multiple drivers. But that's what tells Windows that this app wants to talk to this device. And as part of that, we tell the user that this app is going to access this device. So there's attestation to the user. The user knows what the app can do. Once your app loads, you can use the device information class, windows.devices.enumeration.device-information as a method find all async. You pass this a query. Your query will say find all device basically says find all device interfaces that match this GUID that are currently present. And you'll get back a list of all of the devices that match that criteria, which is probably just your one device. Once you've got that, you open the handle using this create device access instance API. And then that will give you back an iDevice IO control interface. And then with that, you can send your custom commands to the driver. The last two steps are the things that have to be done in C++ code. And our recommendation, and what we've shown in the sample, is that you put that C++ code into its own WinRT component. So write a WinRT component, it's a C++ class, have that class represent your device. Any operations, whatever the primitives are on your device, be methods, properties, events on that class. We recommend this for a couple reasons. One is just general object-oriented reuse goodness. If you if you started out writing a C++ app, so you could get deep integration, and then someday when you need to do a different app or a different company comes in to do an app and wants to use a different language, they now have to figure out what of your C++ code is UI and throw it away, and what C++ code is device related and rip that out and then move it over into something else. So if you componentize it, you make that reuse much easier. The other reason is that by componentizing it, you make it a lot easier to test. And one of the things that's important is that you test end-to-end from your app through your driver. And also you want to kind of test your driver to do operations that your app wouldn't normally do. If your app is crashing, if, God forbid, your app gets compromised, you don't want the driver to compromise the system. So drivers are supposed to be defensive. And by putting this code into a DLL, you now make it easier to test the code. You can write multiple apps that run it. You can even run that DLL from a desktop app and pound on your device driver, pound on the DLL, make sure they're fully functional. This testing is a lot harder if you're trying to do it through your app because now you have to do a lot of UI automation. So let's see, that's the app. And then the last piece is the device metadata. Device from the purposes of the device app. I mean, device metadata does a lot of things, right? It supports device stage. It provides pretty icons for your device and devices and printers. For the purposes of a device app, device metadata is what controls privilege and auto download. So for your app, your device metadata will do two things. It'll most likely declare that your app is the app to be automatically downloaded. It will also declare that your app has privilege to access the device, and there's a property, access custom driver. And since you're using a custom driver, that has to be set to true. If that's not set to true, you'll get an access denied error when you try to open the driver. Thing to note, and I don't know, I imagine this has been mentioned, but one thing to remember is that the permission applied by the metadata applies to the device container. People understand the device container concept. It's been talked about already. I don't see nodding. But, so device container is a piece of plastic. This is my sample device. It's a very simple container. It has one device instance inside of it. A multifunction printer might have 4 or 5, scanning, printing, fax modem, and 3 or 4 USB drive slots. But they all get bundled together into one container. The metadata applies to the container, and the permission applies to every device interface in that container. So in this case, one driver might enumerate a few device interfaces. All those interfaces would be controlled by this. In the case of a printer, which is not a specialized device, but it's a complicated container, in the case of a printer, you have 4 or 5 drivers in there. They might all be enumerating device interfaces. All of those interfaces are covered by the privilege from the metadata. So one reason why you might want to declare 3 or 4 interfaces in your app is that you need to talk to 3 or 4 different devices that have been enumerated as part of your container. So that's it. I mean, that's the 4 components. I'll walk through a little bit about how to actually put the pieces together. But I wanted to we have a few points of design guidance we've come up with. It's hard to do a lot of design guidance here because your driver is whatever you need to do to work your device, and your app is whatever you want your customers to do. So really all the guidance kind of goes in the middle, and some general goodness. So authoring device drivers. If you're going to write a device driver, use Windows Driver Framework. We highly recommend that you use the user mode version of the driver framework. It makes the development a lot easier, makes it a lot faster. And if something goes wrong in your driver and your driver crashes, or if something goes wrong and your driver is compromised and taken over, the damage to a user system is much less than if you had a kernel mode driver. Kernel mode drivers run as part of the kernel. They have access to all memory, all processes, everything. User mode drivers run as local service processes. They have significantly more limited access to users' files and things like that. And then, because your device has to be certified through the Windows hardware certification process, make sure you look at the process, figure out what are the requirements for your class of device. The last thing you want to do is develop a device, be ready to go into certification, and then realize that for your device class, you had to have an MSOS descriptor on your USB device. Or you implemented a particular USB class, but didn't implement some required function that Windows mandates. So look through the certification process, make sure you build it into your requirements up front. If you are porting an existing driver over, or if you're building a new driver and you're going to have some desktop software and a Metro style app, think about separating out those 2 interfaces. Have one interface for the desktop software and another device interface for your Metro style app. and give them different GUIDs and slightly different contracts. The reason for this is that it's good to build that separation in up front, because usually if you're running a desktop app, it tends to be an administrator app. It's more for configuration or some sort of maintenance on the device, whereas the Metro style app would be more for interaction with the device, consumption, things like that. And if you end up in everything on that interface is accessible from the Metro style app. So if you have administrator functions, or if you might someday have administrator functions, having a separate desktop interface in place will make that a lot easier to add on without risking something in the app having access to a functionality that it shouldn't have. And like I said, if you have an existing, another reason is if you have an existing driver that supports a bunch of ioctls, maybe supports read-write, maybe it's not so clean on what each interface maps to in terms of functionality. Creating a specific interface with a specific contract for your Metro style app will just avoid any leakage, any functionality that you didn't mean to let the app have access to, but now it does. Right? Because the apps are per user, they can be downloaded for the store and run without administrator access and things like that. You don't want to leave a door open where some user on a machine could get access to the device in a way that only an administrator should have. So another thing that's problematic here is the updating. We have very loose coupling between these three components, the software components, the app, the device metadata, and the driver. Apps come from the Windows Store. Device metadata comes from the Windows Metadata Server. Drivers come from Windows Update. They have different release cycles, different amounts of time before a posted component gets saturated out into the ecosystem. So we have some guidance in the white paper, which we're working on publishing, which talks more detail about the order to do these things in, but there's a order we lay out for distributing things that I don't remember off the top of my head. But we want to make sure, we want to make sure the drivers get saturated out into the market first, and then the metadata gets out so that the app will always have privilege, and then you can update the app and distribute your app. Otherwise, if you don't do this in the right order, a user can end up in a weird situation where they plug their device in, they get the metadata and the app, but they haven't gotten the drivers from Windows Update yet because it wasn't actually available for automatic download yet. Or you get the app and you get an update to the app that changes something, but you don't get a device metadata update or a driver update with it, and now the app doesn't function. So there's a precise order for pushing these things out into the ecosystem. The other thing, though, is because you can end up in a situation, and you can end up in situations where you might get an app update, but you don't have the driver updated, or you might push a new driver update out, but not think to push an app update out, that you want to make sure you have backwards and forwards compatibility between these things. So if you push a driver update out, V2 of your driver, you should ensure that it runs with V1 of your app. Even if you broke something, right? Even if you changed a contract such that V1 can't function completely, you want to try to avoid completely torpedoing V1 because you have to get V2, until you get V2 out in the ecosystem. Because some users may not decide to go get the app updates. It's going to depend on the cadence for what users do. So this sort of is the cost of this, one of the big costs of this pattern is managing these three components and getting them all updated and keeping everything compatible over time is going to be difficult. Okay. So I was going to do a sample walkthrough. The one difference between a device driver for a Metro style app and a regular device driver that you've already written is that you have to set the restricted bit on the device interface so that you have access. So to do that, can everybody see that? Yeah, I was going to. Hide a bunch of stuff. Is that better? All right, so this is the user mode driver framework driver for this device. It's the FX2 board. The sample is UMDF_FX2. You can find it on NSDN. It's a sample we've been shipping for 3 releases now. We did some small updates to it, and one of them was to make it work with the Metro style app sample for this device. Have people ever seen this board? Okay. So this board is produced by a company called OSR, Operating Systems Resources. They're a training and contracting company. You can buy them from osronline.com. They sell them at cost. They developed this in conjunction with us 10 years ago, I think, 7 to 10 years ago, as a demonstration board. So this is based on the Cypress USB 2 FX2 chip. It's very simple. It has a bar graph. It has some dip switches. It has a little 7-segment display. It has a button that does nothing, I think. It might signal wake so that you can demonstrate wake from input. But we use it a lot for samples because for a long time we were talking about toasters, and there aren't actually reasons to write drivers for toasters, but we have like 6 drivers for toasters, which is very silly. So now we've since used this as our real hardware. And the S means that it's in sleep mode, but I already have the driver installed on here. Anyway, this is the driver, to make a long story short. This is the driver for this device. We have 2 of these. There's a kernel mode version and a user mode version. They have basically the same functionality, just showing how to write the driver in the 2 different models. So this is the spot in the driver. And unfortunately, the driver is kind of layered, but this is the part. During initialization, this driver creates a device interface. It's a method on the FX2 object, which is an object given to the driver by the framework. And so it creates a device interface with this horrible-looking GUID, 573E8, blah, 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 blah. And then, this is the code that we've added for Win8, is you have to set, once you create the device interface actually has a presence in the registry. It has properties that can be applied to it. And so you have to go through, in the UMDF side, there are kernel mode APIs. We use this from the IO manager. In kernel mode and user mode, we go through the Windows driver framework and get the unified property store, and then you set a property, device interface. I have a cable on top of my mouse. Device interface restricted. So this is the property that tells the device broker that this interface could be accessed by an app. Setting it, it's a Boolean type, and it is set, hopefully, is restricted is set to dev prop true. So that's really, it's a lot of lines of code to do a very simple thing, which is to set a Boolean property on this device interface. That is the only change we've had to make to this driver to make it accessible by the Metro style app. The actual driver has a number of files in it that are really just related to operation, and I kind of wanted to avoid getting into them here. So when this device driver starts up and runs, one of the things it does is publish the interface and then set the restricted property on it. And I have the driver on here already, so that's already done. The next thing we need to do is find our demo app. So, like I said, the sample app is unfortunately kind of has a lot of boilerplate in it. I didn't think it was really the most appropriate thing for a demo, so I wrote a ridiculously simple application, which, with any luck, will run. Sure, let's build it. Is that up on the screen? Okay, so I don't know how well you'll be able to see this from the back, but like I said, really stupid, simple application. One button to open the device. Awesome, we got an error. The application is not on the list of custom privilege applications for the container. Any luck? That is because we don't have the device metadata set up. Oh, good. Okay. Awesome. Now I get to demonstrate something else. All right. So the problem is that the driver is setting the restricted property on the interface, but because this is the restricted model, nothing is saying that this app has access to the device. So to do that, we need to use device metadata. Now we have some sample device metadata here. This metadata comes with the sample. And like I said, for device metadata, for the purposes of an app, the only thing that's important is this page, where you'd set the set of applications that are automatically downloaded and the ones that have privilege. One note is that the policy is that you can have one Metro style app for an external device. The sample has 5. This would not pass through metadata certification. But for the purpose of development and demonstration, you can add as many apps as you want into this list. And the one I've added here is my demo app, Demo FX2 app, publisher Peter. And go publish this on the system. So copy packages to your system's local metadata, finish. And elevate. And hopefully, the demo gods are smiling on me. Hey, we have a pretty icon. Pretty is a relative term, I know, but we have a pretty icon. And if I stop the debugger and restart it, yay, this time it's going to work. Open device. All right, so it says S. Now it says 8. I have an application that can talk to my device through my custom driver. And I can show you, let's go through some of the code for this now. Why do I have to build it? All right, so let's go back and set a couple breakpoints in here. Can I get away with 150% in the back? Is that readable? Okay. So I have 2 buttons on here. They have event methods, button click 1 and button click 2. And so button click 1 opens the device. And to open the device, we create a query string. In this case, we're looking for all device interfaces which have this as the class GUID, and where their interface enabled is equal to a very, very long way to say true. Apparently, you can't just use the string true because it gets localized and that messes the query system up. Now, I'm going to be a good boy. I'm going to disable, this is an asynchronous operation, so I'm going to disable my button so that somebody can't click it again while I'm doing a query and kick off another query. I should point out, this is an async method, C#. So this function, when it returns, actually returns a promise for the completion of the whole task. And the reason this is an async function is that I'm going to call an async method, find all async. So find all async, I give it my query string, and let's watch what happens. That gives me a list of devices. There's one device in my device list, which is this one. Let's see. Get the device interface. Device interface has a path. The ID is the path. This is the name of the device interface that an application can use to open it. It's enabled. It has a nice name, FX2. And there's a lot of properties you can query about, friendly name for the device, icon, things like that. So if you want to be able to, well, what you can get from this is the device instance, and then from that you can go find the container, and from the container you can go find the icon and the name and localized name, things like that. But get the ID, and then we're going to call, this is my custom class. This is written in C++. FX2.device is the class. It has a static from ID method. We hand it the path. and that'll make my device. And that's it. Now I have an open handle to this device. Change number. Again, the fx2.device class abstracts everything I can do with my device. In this case, I can do one thing. I can show a number on the screen, on this screen. There we go. So the app side of it is fairly simple. It can get pretty complicated. The custom device access sample shows a lot more detail about how to set up a device watcher so that you can respond to plug and unplug events. It shows how to handle asynchronous operations. So I demonstrated setting this display as a synchronous operation because I know it takes a very short period of time. In general, but I'm doing this on the UI thread. If that had taken any longer, I would have locked up my application for seconds. The user wouldn't be able to interact with it, and it's very possible it would get terminated if the user tried to flip it in the background or something like that. So for any long-running application, I can't remember what our threshold is, but I think it's a couple milliseconds. The recommendation is to put it into, make it asynchronous. And so the sample app will show how to do I/O operations that are asynchronous. It'll also show how to do events from your device back up to your application. For example, when you flip the dip switches on here, you can get an event, an interrupt. There's an interrupt pipe that services this. So when we flip these, an interrupt message comes back to the PC. The driver watches for those interrupt messages and will complete I/O control operations when they occur. And then the application, the class turns those into event notifications for the application. I wanted to go through, so that's the app part of it. The WinRT class is also fairly simple. Really make that 200% also. All right, so here's our WinRT class. We have one public static method, which is a constructor method. We have one public method called showNumber. Internally, it keeps track of the iDevice control interface, and it has a private constructor to set that up. And then from ID, remember from ID gets the path, so it calls create device access instance with the path. Tries to get read and write access to the device, and it gets back a I create device access async object, and then for the purposes of the sample, we're cheating and waiting synchronously for that to complete. Again, I know that this driver takes very little time to complete open operations. If this were a device that had to do a significant amount of work, whenever the driver did a significant amount of work whenever somebody opened it up, for example, had to communicate with the device, share a password or something like that, you would want to model your from ID as an async operation. So we wait for the open to complete, get the result, which is our iDevice control interface, and then we create a new device and return a reference to it. The constructor just stores that interface pointer away. And then the showNumber method, which shows the number on the screen, just does a synchronous device control. So iOctal OSR USB FX2 set 7-segment display is a private control defined by the driver. It's defined in public.h, which is a header file that's shared between the C++ DLL and the device driver. So this header can be whatever you want to name it, but this header defines the interface for the driver. In terms of I/O controls, so you can get the configuration descriptor, you can reset the device, get and set the bar graph display, read the switch state, get and set the 7-segment display, get messages whenever the dip switches are changed, and then the user mode version of this has an option to play a string to the 7-segment display. I don't really remember what that was supposed to demonstrate, but we added it. Right, so device control sends the set 7-segment display, gives an input buffer, which is the byte that it was provided with the size of 1, no output buffer, and then if that fails, we throw an exception. So this is a very simple iOctal. Takes some data from the application, convert it into a format the driver can understand, send the command to the driver, let the driver do its job. So I was trying to demonstrate as little, like minimal amount that's needed in order to be able to start talking to your device. What I found in dealing with this model and working with the sample is the hardest thing is this first command, getting one command to your device, getting your privileging set up, getting your metadata installed and your driver loaded. And once you can get here, then you can start to build on things fairly quickly. So that's what I was sort of trying to demonstrate, that fastest possible path to the device. Got about 10 minutes left probably. I think we can go over a little bit if there's questions. Just if I can summarize real quick. So this is the most flexible pattern, can handle any device, only supports the restricted model. It's a costly pattern in terms of development of device driver, certification of the device driver, and ongoing maintenance. And you need to be very aware of the compatibility between your components whenever you're doing updates. But for a fairly large set of devices, this is probably the only pattern that applies. And we're hoping it will let you guys write really good apps. Does anybody have any questions? Sorry, I know it's kind of a lot to. Does anybody have, who has devices that this pattern applies to, do you think? Okay. What kind of devices are they? Like USB, Bluetooth? Okay. Can you tell me what it connects over? Can you tell me what bus it connects on? What bus does it connect on? Okay. And yours? You have USB? Okay. No, I wrote this sample last night at 1 a.m., so I imagine it shows. No, I was going through the complicated sample last night, which I don't think will run here because I don't have the metadata set up. So if you search for custom device access, custom driver access, you can get the full version sample. But their samples have a lot of boilerplate template in them, and I just thought that was going to be sort of too much code unrelated to actually talking to the device. So I didn't want to use it. But if you want a copy of the app, you're welcome. I can copy it onto your computer for you. So. Okay. So I'm going to be around for a while. I think we're going to talk next about the internal devices and OEM systems. So if you got any other questions, let me know. Thank you.